Hello there, my name's Richard Arundal and thank you very much for taking the time to watch this video. In this lecture today then, we're going to delve deeper into the material handling side of on-orbit manufacture and in particular the acquisition and storage of materials. So, hope you're comfortable. Let's get started with the lecture. In this lecture video then, we're going to revisit a top-level technology roadmap which may or may not be familiar to you. We'll then look at briefly introducing the material handling system process and how it fits in to the wider on-orbit manufacture process. We're going to then look at how we can acquire materials, whether it's from Earth or from space environment. We'll then look at how the material could be stored and then briefly cover some technical challenges that face us. Let's start the lecture then by reintroducing the top-level technology roadmap. For any manufacturing process, whether it's in space or on Earth, handling the material and making sure that it arrives at each stage of the manufacturing process is critically important. As we can see from the roadmap diagram here, the material handling section is what we're going to be looking at for today's lecture. In this version of the technology roadmap, we can see large green arrows extending out from the material handling box, and this is to represent how material handling is present throughout the entire on-orbit manufacturing system. If this technology roadmap is not familiar with you, then please check out the Introduction to On-Orbit Manufacture video. The link will be below in the description. Let's take a closer look now at the material handling system and break it down so we can understand how it fits in to the whole concept of on-orbit manufacture. What we can see now then is the material handling system and the flowchart that links all of the different processes together. The on-orbit manufacturing system is no different to any other manufacturing process in the sense that we need to first acquire materials and store them safely. We must then move the material from the storage into the manufacturing process of choice. Once it is then manufactured, we must then validate and carry out quality checks to make sure that what we've manufactured meets the required standards. And then finally, we look to dispense and deploy the product. You will notice that from the validation and quality checking process, there are three potential routes for a product once it's manufactured. That is the dispensation and the deployment, which means that it's passed its quality checks. A second alternative is that the product doesn't quite meet the requirements, but there's opportunity to rework or recycle the material, in which case it can get sent back round again to the beginning of the process. And thirdly, the product is manufactured so badly that it would need to be scrapped and disposed of. In the case of an on-orbit manufacturing facility, as in if we imagine it being a space station or an orbiting factory, disposing of materials in the space environment is certainly unwanted and it would contribute to further space debris. The problem of space debris, or space junk, is a growing one, and it's up to the on-orbit manufacturing facility design to ensure that disposal of materials is carried out responsibly and minimalised so that this problem is not further exacerbated. In this video, we're going to be focusing further in the material handling system, specifically at material acquisition and storage. The other processes will be covered in future videos, and as part of the Introduction to On-Orbit Manufacture series, material handling is covered as part of the other systems as well. But by all means, please like and subscribe to keep in touch with new videos as they get released, and you'll be able to follow along with the research as we delve into these new areas in the future. So let's imagine now that our on-orbit manufacturing facility is in fact a space station that might be orbiting Earth, the Moon, or wherever the mission might take it. So how would we get materials to this space station of ours? In our context then, we essentially have two possible routes of material acquisition, and that is Earth-based materials and materials available in the space environment. For materials that come from Earth, this is the conventional processes that we are very accustomed to in day-to-day life, such as mining, factories that produce materials, and even recycling. What we'll notice as well on this diagram up on the screen now is that spacecraft salvage sits in the middle with the dashed line between Earth and the space environment. This has been included this way in the diagram because spacecraft are initially manufactured on Earth using Earth materials, but then once they reach the end of the life in the space environment, then technically they can also be salvaged and therefore become part of the space environment, or perhaps they re-enter the Earth's atmosphere and whatever doesn't get burnt up may have some hopes of being reused. As humanity perfects the techniques and engineering to land on other worlds and asteroids, such as with recent missions, there opens the possibility of space mining, which is to extract raw materials from planetary surfaces or even asteroids. Now that the different sources of materials have been introduced, let's take a closer look at each of them now. The materials used in spaceflight are carefully chosen and designed. Regardless of whether it's a metal, plastic, composite, ceramic tile, or even a honeycomb sandwich style of structure, they must be qualified to a high standard. A spacecraft is very complex and made up of many different materials depending on the system, and each of these systems has their own requirements. For example, a spacecraft structure must not only be as lightweight as possible, but also designed to be as strong as possible and to survive the launch environment, the initial takeoff from Earth into space, but it must also survive the space environment. Different requirements are laid out for ceramic tiles. For example, they might be used for missions that go closer to the Sun as a form of thermal shielding, or they might be used on re-entry vehicles like the shuttle was underneath, as we could see in the picture at the bottom right-hand corner. Material selection and spacecraft structural design is a very complex area and beyond the scope of this video, but what I do look forward to in the future is to create a space engineering series of lectures, and this will definitely be amongst the topics covered. What we can take away from this discussion, though, for this lecture, is that the requirements to build a spacecraft with these materials would be different to supplying them in, say, for example, a storage module and sending them up into orbit. This is because a payload of just materials for an on-orbit manufacturing facility doesn't have the same structural requirements as it would for a conventional spacecraft, which needs to survive the launch environment so that the payload isn't damaged, the payload being the electronics or the antenna or the telescope. Therefore, once a spacecraft has actually reached its destination orbit, the structure's purpose is to hold the spacecraft together, and that's what it will do for the rest of the spacecraft life. Of course, it has to survive the space environment and it will be designed for that, but the launch environment compared to the space environment consists of different mechanical loads. Therefore, on-orbit manufacture using materials and building components and structures in space opens up the opportunity for creating some very interesting geometry and products that we couldn't normally build in an Earth environment. This payload idea then of launching material to an on-orbit manufacturing facility doesn't just include raw and pre-made Earth materials, but it could also apply to recycling as well. On-orbit manufacture provides an opportunity to repurpose some of the plastic waste on Earth. Plastic recycling, then, could provide an excellent source of material for manufacturing purposes and would be fairly easy to store and launch from Earth up to an orbiting facility. If recycled plastic could be engineered so that it can survive the space environment, then there's plenty of opportunity to create structural components using this material. One example of how this might be achieved is to compress the plastic waste into a block, like in the picture shown on the slide here. With such a block of recycled plastic, different opportunities to then manipulate this with manufacturing process present themselves. For example, there could be a lengthways cut and you could create panels, or perhaps you could machine shapes out of it and essentially sculpt your desired geometry and components from the block, removing the excess and leaving behind the shape and product that you desire. Moving on now to a different form of recycling, let's take a look at salvaging spacecraft. Space debris in low Earth orbit is a growing problem, so if there's a way we could somehow salvage this debris and repurpose it, that would be beneficial not only for the local space environment, but also for the on-orbit manufacturing facility. A lot of the space junk that is currently in low Earth orbit is difficult to collect and recover, but there are concepts for some of the larger pieces and potentially derelict satellites that are obviously no longer in use and have been sent out to graveyard orbits. Some of the concepts that are being developed at the moment for recovering these derelict spacecraft include the concept of nets, which would be fired out to capture a spacecraft, and then once it has been netted, it would be pulled in so that it is easier to control. A variation of the net concept is the harpoon, which would be fired at a spacecraft, and once it is penetrated and attached onto the target spacecraft, it would then also be dragged in via a tether and controlled, and then from there parts could be salvaged. Regardless of how a derelict spacecraft would be salvaged, it provides an interesting opportunity for on-orbit manufacture in terms of gathering materials for manufacturing processes. Let's take, for example, salvaging a fuel tank. By salvaging a fuel tank, what we have done there is created an opportunity for a resupply mission and combining this with on-orbit servicing processes. If we were to follow this logic and apply it perhaps to other spacecraft systems that could be salvaged, then not only would this help with the space debris problem, but it could also cut down costs for future spacecraft missions. Let's take a look now at the last method of material acquisition in the space environment. As humanity looks to explore the stars and colonize new worlds, the opportunity to gather resources from other planets and asteroids presents itself to the on-orbit manufacturing concept. Space mining in particular has gathered interest in recent years, and this has the potential to supply raw materials for construction projects. Raw materials, however, often require processing before they can be used to their full potential. A facility that could process raw materials, for example on a moon base, would have a fantastic synergy with on-orbit manufacture. With upcoming projects such as the Artemis mission, humanity is starting to pave the way to explore and colonize the moon, and so in a few decades there is the potential for such a facility to exist and for on-orbit manufacturing to gather momentum and demonstrate technologies. Other opportunities for space mining include asteroids, where recent missions such as the Osiris-Rex have gone to explore the Bennu asteroid and determine its material composition. With the sample collection of the Osiris mission being successful, this paves the way for future probes to carry out analysis for the purposes of space mining and resource extraction. So now that we have looked at ways of acquiring materials for on-orbit manufacture, how would we go about storing them on a spacecraft? At a top level, we have two choices for storing material, that is internal and external. If we were to store material for on-orbit manufacture internally, then some of the benefits that we would get from this is that we would have more protection from the space environment, so that would include space debris, the harsh radiation from the sun, and so forth. We'd also have better control of the material, and that's in terms of centre of gravity of the whole spacecraft, and of course moving the material from one system to another in the manufacturing process. And it is likely that we could make the process very efficient in terms of using the material if it is internally stored, for example with the stock material. We must consider, however, some of the disadvantages of storing the material internally, and that is docking and resupply complexity. So if we have a spacecraft coming in to resupply, then the rendezvous point and the attachment and transfer is quite complicated. And we're also limited by how much the spacecraft itself can hold within its payload. This payload volume limitation would apply not only to the on-orbit manufacture facility itself, but also the resupply spacecraft. So it might need several missions from a resupply vessel to provide material for the on-orbit manufacture facility, which would increase costs and increase complexity of the overall mission. What about externally storing material from the on-orbit manufacture facility? So with the facility orbiting in space, we have the potential for a very large volume of material able to be stored. We essentially have as much of the nearby space environment as we could use, within sensible reason, of course. And we also have the opportunity to use nearby surfaces, let's say for example a moon, planet or asteroid that the facility may be orbiting, and this could act as a sort of warehouse or depot to collect the material from. Some of the drawbacks, however, of storing material externally to the spacecraft would be that there are collision and detachment risks, and we wouldn't want the material, for whatever reason, to drift off into space, because that could pose all sorts of problems. Storing material externally also increases the complexity to the material supply process. So if you imagine that we've got our material stored outside of our on-orbit manufacture facility, then we would probably need something like robotic arms or some other system to then transport that material and feed it into the material system of the on-orbit manufacture facility. Of course, as well, we've then got the exposure to the space environment, so we don't want the material to degrade while it's being stored, as this may lead to mechanical property changes and therefore rendering the material useless and unfit for purpose. Let's wrap this lecture up now with a very quick look at some of the technical material storage challenges that we face for the on-orbit manufacture system. As we can see on this slide, these are just some of the technical challenges that present themselves for the storage and acquisition of materials for on-orbit manufacturing. For the space environment, technical challenges that include mechanical failure and mechanical damage are present, and so techniques such as shielding or providing a stable environment for the material should be considered to protect against some of these phenomena. The material that is chosen for use in on-orbit manufacture must also be considered as part of the design process, and that will consider the material's mass and mechanical properties, what sort of products that the on-orbit manufacturing facility is aiming to produce, and it must also be compatible with these processes. The material must also be compatible with the storage environment that is selected, which would be part of the space environment design process. For the system design aspect, we must consider material alignment and its transit speed through the system. We must also consider jams and blockages and how might we recover from those situations, and that would lead into the synchronization of the system as a whole. We must also consider what would happen if the material were to break or tear during the process, and how might we recover from that as well. All of these different considerations will be covered in future videos as part of a space engineering series of lectures. I can, however, fully recommend a particular textbook that has helped me in my own research and would provide much more technical detail in this particular area. Materials and Processes for Spacecraft and High Reliability Applications by Professor Barry Dunn. Some of the chapters in this book consider spacecraft material requirements, materials in product assurance, failure prevention, and material analysis and an assessment of post-flight materials, which in particular discusses how the space environment has an effect on certain materials. A link for this book can be found in the descriptions below. To recap this lecture video then, what we've done is we've revisited the top-level technology roadmap. We've then briefly introduced the material handling system process before looking at how the on-orbit manufacture facility could potentially acquire materials. We then thought about how these materials could be stored, whether it's inside or external of a spacecraft. And finally, we've looked very briefly at the technical storage challenges that are presented to us with the concept of on-orbit manufacturing. That's the end of another lecture in this introductory series. I hope you found it enjoyable and useful, and if you'd like to subscribe and press the like button, then there'll be plenty more videos coming out. But until next time, thank you very much for watching this video and hope you'll join us again soon.